Welcome. We have arrived to deep learning in this course of artificial intelligence for autonomous driving. The concept deep learning emerges as the amount of layers in neural networks reaches exceedingly big numbers. So the resulting networks have billions or trillions of parameters to train, and they are often trained with big data, trillions of data as well. There are many models in deep learning depending on the application we're dealing with, but I have chosen to explain convolutional neural networks for they are the most powerful models in computer vision to recognize objects or analyze data from videos, and therefore are among the most useful tools in autonomous driving. Welcome again. Convolution is a mathematical operation on two matrices that produces a third matrix expressing how the shape of one is modified by the other. In practice, you overlap the kernel matrix with the top left corner of the other image and perform the dot product between the kernel and the overlapped portion. The result is a real number that will serve as the first component of the resulting matrix. And the rest of the components will result from repeating the same operation as you slide the kernel all the way to the rightmost and all the way down to the bottom. Let's see. Now, since the center of the kernel is displaced 1 pixel at a time, we say that this particular convolution has a stride of 1, but it could actually be any stride we wish. Here, a more complete example with a kernel of the same size, although a smaller convoluted image. The original matrix is just the bright blue part here, and notice that its edges have been added with zeros so that the resulting matrix is the same size as the original. Without this zero padding, the resulting matrix will necessarily be smaller because the edge pixels will never have a chance to host the center of the kernel without part of the kernel slipping out. As a result, the border information will be lost in the resulting matrix. For example, this resulting matrix has no zero edge information and is therefore smaller than the entire padded matrix. Accordingly, the size of the resulting matrix depends on whether padding is applied or not, and also on the size of the stride, which in this case, as you see, is also 1. This is, the kernel moves 1 pixel at the time. The importance of convolution in image processing is that depending on the kernel we apply on an image, we can get certain features that may or may not be useful for its recognition. For example, when we use this kernel on this particular image, the resulting convolution is an image that gives us the horizontal edges of the original image. Just for illustration, here we have zoomed in on the multiplication of the kernel with this chunk of the image, the result of which is minus 183, just this value here. But again, depending on the kernel, we will get different features of the image. And since we don't know what features are the best to recognize a particular type of images in a given problem, the idea behind convolutional networks is to treat the values of the kernel as parameters to be learned. And of course, we will not use only one kernel, but a set of many kernels. And by letting convolutional networks fine-tune the values of these kernels as weights, convolutional networks have proved to be capable of detecting and learning low visual features shared by images of a same class, say cars or dogs, that will be otherwise seldom noticed by the human eye. Now, it is possible as well to perform convolution with volumes. It works almost the same. You place the volume kernel in the corner of the other volume and start taking the dot product of the overlapping parts and sliding the kernel across the width, the height, and also the depth if necessary. In this particular case, we don't need to slide across the depth because both volumes have the same depth, and that is also the reason for our result to be bidimensional, not a volume. In fact, in convolutional networks, every time you perform a convolution with volumes, they need to have the same depth or number of channels, 3 in this case, to produce a bidimensional output. We will check that later. Now, if you want your output to have more than one channel, you can very well have as many channels as you wish just by convoluting your input volume, that in this case could be an image with 3 R, G, and B channels, with as many volume kernels of the same number of channels as you want. In this example, there are 2 kernels and the outputs are, of course, 2 bidimensional matrices. And at this point, this setup could be seen as a one single layer convolutional network where this is the input, this is the output layer, also the only one, and this is the output that for some reason we wanted it to have 2 channels. It actually depends on the problem. The only thing that we need to add to each output before they become actual outputs is a bias, value, and as well as the transfer function assessment that for most cases in convolutional networks is the ReLU function that we already know. So this could be seen as the net values of the layer or the raw outputs, while this as the actual outputs of the layer. We said that this is a single layer convolutional network, but in case it wasn't, this output will be fed as the input to the second layer and so on. And the kernels in the second layer, no matter how many, they would need to have 2 channels to process this output. Also, back in this layer, remember that the values of the kernels will result after training because they are the parameters or weights to be learned by the network. In this case, we have a 3 by 3 by 3, 27 plus other 27 weights to fine tune. That makes a total of 56 parameters if the 2 biases are also taken into account as they should. Now, let me talk about the efficiency of convolutional networks. Here we have a single layer perceptron with 25 inputs and 9 outputs. Since this is a classic densely connected network, it has a total of 25 by 9, 225 weights. On the other hand, let's see the simplest convolutional network with a one-channel input of 5 by 5 and a one-channel 3 by 3 kernel in the only single layer that it has. Also, the output is a 3 by 3 matrix. If I wanted to translate this convolutional network into a classic fully connected perceptron, the first thing I need to do is to flatten the input into a single column vector. Then, the kernel that has only 9 values will be attached to 9 values of the input like this. And then I would slide the kernel 1 pixel, 1 more pixel, 1 more, yet another more, and so on until I get the 9 values of my output. Notice that the number of weights to be learned in this model are surprisingly 9 only. This is because there is only one kernel. So be aware that neurons in convolutional networks are not represented by kernels, but by the movements or displacements of the kernels. Every time a kernel moves one position and performs a dot product, it produces an output, the output of a single neuron. But the good news is that many neurons share the same weights because their outputs, of course, are produced by the same kernel. Accordingly, even though we have 9 neurons the same as here, we only need to fine-tune or learn 9 weights versus 225 here. And even better is that to calculate the output of each neuron here, we would need to multiply 25 numbers, while in convolutional networks, only 9 numbers need to be multiplied per neuron. This makes the convolutional networks to be way more efficient than classical fully connected networks. In our previous example, therefore, even though our layer has 2 kernels, the number of neurons in that layer is equal to 4 by 4 plus 4 by 4, 32 neurons. And this is because this kernel made 16 moves during the convolution with the input to produce this 4 by 4 partial result, and this other kernel made 16 too. Remember, number of neurons is equal to number of dot products or kernel movements performed during the whole convolution. Now, it is time to introduce you to a more general model of convolutional networks. Here we have a convolutional network with 3 layers. The input is a volume with n channels. In the first layer, we have k kernels with n channels each, so they can be convoluted individually with the input. Therefore, the output of this first layer will have k channels too. Similarly, in the second layer, we choose to have s kernels with k channels each. Accordingly, the output of the second layer has s channels as well, and therefore the kernels in the third layer need to have the same size s. Finally, as we have u kernels in the last layer, the output of the convolutional network will necessarily have u channels. Now, suppose that all the kernels in all layers are 3 by 3. They can be any size though. And the size of the channels in the input is 1024 by 1024. If we use no padding, this output will be 1022 by 1022, and this other will be 1020 by 1020, so our final output will be 1018 by 1018, too big. Notice that in many cases, the output of a neural network is just a single number or a small vector representing a class. Therefore, sometimes we would like the size of these internal outputs to decrease faster, so in the end we have a rather small output. To this end, we have 2 common practices in convolutional networks. First, we can implement a pooling layer that applies a sample-based discretization process. The objective is to downsample an input, reducing its dimensionality. In this case, the pooling operation reduces to a half the size of the input just by keeping the maximum value in all 2 by 2 independent patches of the input and eliminating the rest. So a pooling layer has no parameters to be learned, and it is just an operation applied to the output of a convolutional layer just before the ReLU function is assessed. For the sake of readability, I did not put here neither the biases nor the ReLU functions, but we already know that they are needed in the output of each convolutional layer. So, if we apply a pooling layer to the output of the first layer, the output will be reduced to a half, and so will the output of the second. Now, if we apply another pooling to the output of the second layer, such will be further reduced, and so will the final output of our network. And if we apply yet another pooling layer to the output layer, the final output will get dramatically reduced. And having reduced the final output this much, now another strategy to keep reducing is to apply a flattened layer. The flattened layer has no weight to be learned either, and its only purpose is to convert the output volume into a flat vector. In this case, one of size 127 by 127 by u. Now, since we have a flat output, such can be very well fed into a regular, fully connected neural network with as many dense or fully connected layers as we wish. In this case, we only added one dense layer. Notice that by doing so, we can take the final output of the convolutional network down to a single number, perhaps a binary number representing two classes that the network was tasked to learn or classify. In fact, the possibility of adding these dense layers and treat the convolutional network as a regular network at the end is what makes it possible to do transfer learning. What I mean by transfer learning is that very often these convolutional networks are giant networks with billions or trillions of parameters that cannot be trained in regular computers at home. So companies like Google or Nvidia have already pre-trained models that we can download and use to solve our particular classification problems just by adapting the output to our needs through a regular fully connected network. Some of the most famous pre-trained convolutional networks are VGG16, GoogleNet, AlexNet, among many others. Now, just to conclude, I want to say a word about the training of these networks. They are trained with the same backpropagation algorithm as all other regular networks. So for training, you have to apply the forward step and then go backwards, updating the weights as usual. Let's see a bit of how it works for this specific convolutional network. A 32 by 32 by 3 input is convoluted with 4 kernels of 3 by 3 by 3 to produce an output of 30 by 30 by 4 in the first layer. Do not forget bias and ReLU. Then this output is convoluted as an input with the 2 5 by 5 by 4 kernels in the second layer to finally get a 26 by 26 by 2 final output for the whole network. Again, bias and ReLU were assumed in the calculation. Now, to update the weights in the second and final output, we will use the backpropagation formula to perform the backward step. We need to find the delta E with respect to the weights of the second layer. But delta E can be expressed as delta E with respect to Z2, the net of the second layer, multiplied by the output of the first layer transposed. And this delta E, we know it because it is in the output layer, so it is defined as minus the error times the derivative of the ReLU function with Z2. So when we replace this term in the first equation, we have this. Now let's verify it is correct. The W2 we are looking forward to updating is a parameter of size 2, 5 by 5 by 4, you can see it here. So this delta term has to be of the same size for the equation to make sense. And if we see this term comes from the multiplication of a 30 by 30 by 4 array with this term, which in turn comes from the multiplication of two arrays of 26 by 26 by 2 each, which produces as a result another 26 by 26 by 2 array. So that is the size of this array here, and this convolution yields two arrays of size 5 by 5 by 4, just as we were looking for. So this equation makes all sense now. In short, all we need to do is a convolution of this array with the first channel of a slightly modified version of this other array to find the new values of the first kernel in the second layer. And if we do the same convolution with the second channel, then we will get the values for the other kernel in the layer. So all the weights are finally updated. In pretty much the same fashion, you can continue to update the weights of the first layer, but actually you will be seldom asked to perform this updating by yourself. In practice, we always use high-level libraries such as TensorFlow in Python to train convolutional networks. TensorFlow is also meant to handling with efficiency all these dimensionalities in convolutional networks, such as n kernels with k channels with x by y size and so on, because in mathematics such are known as tensors. So in the end, I mentioned the math behind the algorithm just to remind you the importance of backpropagation in artificial intelligence in machine learning, but you don't really have to worry about it by now. As a final assignment for this course, I want you to experimentally prove why convolutional neural networks are said to derive their respect and reputation in autonomous driving from the fact that they can learn visual tasks in the same fashion as biological brains do. In 1981, David Hubble and Thorsten Wiesel, two young neuroscientists, elucidated the way how neurons in the visual cortex encode visual information. They put microelectrodes in the cortex of anesthetized cats and recorded the activity of individual neurons. What they discovered was that those neurons are extremely specialized both in space and orientation. This means that one particular neuron only fires when a specific pattern is detected in a specific part of the visual field, and therefore no other pattern, and not even the same pattern in another part, can make this neuron fire. For instance, if a neuron is linked to this part of the visual field and it is specialized in detecting this orientation, it will only fire when the bar crosses such area of the visual field. Well, in this assignment, we will build a convolutional neural network to simulate a cat's brain, and we will see that the same phenomenon is found in early layers in convolutional neural networks. This is different neurons devoted to analyze different patches of the input image will be activated only when a specific pattern appears. For more information, please refer to the Jupyter notebook associated to this lecture.